So this is the AI and creativity talk, and this is for cognitive systems, and we're going to have a lot of fun tonight. Who am I? Hello, my name is Reed. I am a comp sci educator. I work at Gearing Up here out of campus, and I'm also a web developer for them. And I am a cognitive systems grad myself. I graduated in 2021 from the psychology stream. And I also was a Cogs TA for a really long time. I TA'd Cogs 300 6 times, and that course is near and dear to my heart. So what are we going to be doing tonight? So we're going to be doing a 2-hour talk tonight. First up, after this intro, I'm going to talk about creativity a little bit. We're going to ask some questions. What is creativity? After that, we're going to ask, what is AI? We're going to go through everybody's favorite perceptron. If you've taken Cogs 300, that'll be review. If not, then you might get to learn something new. After that, we're going to be going through an activity where we are actually going to be making collaboratively a choose your own adventure story using some AI art generators for some fun. After that, we're going to break down what we just did. How did these things actually work? How did they make this art for us? And then we'll go into careers in AI and how you can start to get involved in this wonderful place. And finally, we'll end off with a discussion about the various ethical dilemmas that these things arise out of these topics, which I think are plentiful and very interesting. So hopefully we're going to have a nice, fun night here. Is there any questions or comments or anything like that before I begin? No? All right. So let's dive into our first section here then. What is creativity? So one of the traditional definitions of creativity here is kind of a romanticized view of it. This is something that you'll hear in pop culture a lot. And it's kind of this idea that creativity is some kind of expression of this innate genius or this insight. You're channeling something that's maybe from a divine source, and you're really just kind of channeling this creativity out of you. And while that is a wonderful poetic description of what creativity feels like, it gives us very little in the way of understanding the actual cognitive machinery that is happening at place. And so there is a lovely researcher named Margaret Bowden who kind of came up with a more cognitive definition of creativity. And so her thesis is that creativity is the ability to come up with ideas or artifacts that are new, surprising, and valuable. And there's 3 methods for how you actually go out and create this creativity. So the first one here is combinatorial creativity. There are types of creativity. So this is something that involves coming up with new and unexpected combinations of existing ideas. So you're taking something familiar and then you're kind of reinterpreting it in a new way. So you can kind of think of this as like an analogy would be a lovely form of creativity. You're kind of taking something familiar and you're then presenting it in a new light. You're giving it kind of a different way of doing it. Different collages, like if you put together a bunch of different images, that's a form of creativity. You're kind of taking things that already exist and sticking them together in one place. There's also exploratory creativity. And so this involves with coming up with the unexpected ideas as a result of exploring the possibilities of a space. And so usually like you're working within a specific style or you're working with a specific medium and you're finding new ways, new unexpected ways of utilizing that medium. So think of somebody that maybe uses paint in a new style somehow. Like you're using the same medium of paint, but suddenly you're doing it in a different way and it kind of unlocks this entire new space of possibilities. And then you are also doing transformational creativity. And so this comes up with a new idea, which is previously thought to be impossible. So it's kind of related to exploratory. And this is as a result of exploring all possibilities. So this would be coming up with like an entirely new tool. So instead of paint, you can think of coming up with AI art, might be an entirely new form of transformational activity. You're taking something that was previously thought not to be possible, and suddenly you're doing it and you're showing a new way of doing it. So as we move through tonight, I encourage you to keep these definitions in the back of your mind as we explore this question of AI and creativity and whether or not these things can be creative. But I do want to pause because that was some some of the heavier content for tonight and ask, are there any questions so far on these definitions? Yes, that is a really good question, and you'd have to start Googling that. I'm not immensely familiar with the history of this research, but that is a really good question. And if that's something that you're curious about, I encourage you to go and explore it. And I'm sure that there is an answer that's out there, although I do not know it off the top of my head. Ooh, would I be able to echo the question back when I start answering? Yes. Yes. The previous question was about Margaret Bowden and asking if there was basically, as I understood it, like a history of research there that Margaret Bowden was drawing from, or whether this was something that she creatively generated herself, and kind of like what the existing frameworks were there. Is that the question? Great. Yeah, that was the question. And I don't know the answer. You should look it up. That sounds wonderful. Okay. What is artificial intelligence? I'd love to get some audience participation here. What do you think artificial intelligence is? Okay. So I kind of got 4 things from that. We create it, right? It can adapt to its environment. It has goals, and it has some way of accomplishing those goals. Yep. Is that roughly what you're talking about? Okay. Yeah, that's a nice framework. Any other definitions out there? Okay, so you're using humans as a benchmark here. Is that correct? You're kind of like as a comparison to humans. Oh, interesting. Okay, so what I'm understanding is we've taken kind of like traits and aspects about humans, and then we're taking those traits and we're putting them in robots. Yeah. And you're still saying these are kind of human traits that we've taken, and we're just kind of instantiating with a different medium. Is that right? Yeah. Okay, that's an interesting one. Let's see if we can get one more definition. Yeah. A system that can learn. Ooh, I like that. Nice and short to the point. My definition is actually kind of closer to the third one here, just as a quite broad definition. I don't think that any of the definitions here are wrong. We kind of saw different levels and different perspectives on this. So I really like this. I want to talk a little bit about the algorithmic side of artificial intelligence. How does this actually fit into like a computer science framework? So first off, we start with algorithms. So these are just a series of instructions which can be repeatedly performed to accomplish a task. This doesn't necessarily have to be in a computer. You can give somebody a set of instructions for how to tie their shoe, and you could consider that an algorithm. But traditionally, we kind of consider algorithms very integral to computer science, and basically any code that a computer is running can be considered some kind of algorithm. It's a set of instructions. Then we have artificial intelligence. And artificial intelligence here I've broadly defined as the pursuit of machines which are able to autonomously perform tasks at or above human levels of competence. As we saw, there are a lot of different definitions of AI, but this is just one of them. And I did this to contrast it with machine learning specifically, because these two get confused a lot and they are different things. So machine learning is actually a subset of artificial intelligence, in which a computer can learn how to perform a task without having to be told every step by a human. It can kind of infer or learn steps by itself along the way. This type of machine learning has really exploded in the last decade or so, since about 2010. And it is, when you hear the term artificial intelligence anywhere in the media, they're usually talking about some form of machine learning. So how does this actually work? And so I want to talk a little bit about artificial neural networks. So the way that these broadly work is that you have some kind of set of inputs which come in your input layer, and then these inputs get transformed somehow, they get manipulated, and then you have an output layer which gives you the answers. And what's really nice about this is that this layer between the input and the output is something that the computer changes by itself. And it changes usually in a way where it gets better at the task that you're trying to get it to do. And these were really inspired by neurons. So in the 1960s, we created something called a perceptron. Again, if you're taking Cogs 300, this will be very familiar to you. And a perceptron is kind of like an artificial neuron, where you have a set of inputs and then some kind of threshold for activation. And then if that activation is reached, you send a signal further into the network. And the way that a perceptron works is just kind of a mathematical instantiation of this, where you have a set of inputs and you have this neuron or this activation function, And what you do is you multiply each of your inputs by some kind of weight, and then you sum them up. And if it's greater than some kind of activation function, then you might give something like a positive one. And if it's less than, then you might give a negative one. I just have a very simple algorithm for it here at the bottom of the screen, where basically you start with your 0th input, you multiply it by the weight of the 0th weight, you add the then 1 weight to the 1 input, you multiply those together, and you keep doing this for as many inputs as you have. You add them all up, you get some kind of number, and then you compare it to something. And depending on that comparison, that will affect what type of answer you give. Now, this is sometimes a lot easier to understand if you actually have a visual example. So I'm just going to take you through a very simple base case of what a perceptron is doing here. So let's pretend that I have 2 inputs in a neural network, and I want this network to tell me, is something an X or is it an O? And so what I can do is I can represent these inputs in a graph. And what's happening in a perceptron is it's creating a line, it's creating a decision boundary. And so we can represent this with just our typical line equation. You might have seen this in like grade 8 math. You have your typical y equals mx plus b, and we find that by taking our rise over run, difference between 2 y points, difference between 2 x points, find the slope, and then add whatever your y-intercept is to it. But there's an alternative way of doing a similar equation where you turn it into an inequality. And this is closer to what a perceptron is doing, where instead of just drawing the line, you already have your slope, you already have your weights, and then you add in an x and a y, and you figure out, did it fall above or below my line? That blue dotted line there would be what it would look like if my slope was 1 and my y-intercept was 0. This is like the most basic case ever. You can imagine that here with my weights, this weight is 1, this weight is 1. So it's basically just taking the inputs and directly putting them into my network here, where I can then look at those points on my graph. I can look at the x and o and figure out if it falls above or below my line. So let's look at this second equation here. We kind of have y times rise minus x times run minus b. Now our rise and run are both equal to 1. We can just ignore that basically. And we can also ignore b because it's 0. Our y-intercept is 0. So we basically have y minus x. And we have to figure out, is this above or below our line? Is it above or below 0? So if we take our x, our green x there, we have 8 minus 4 equals 4. Woohoo, that's a positive number. That means we classify that as an x. Is this a correct classification? Yes, right? That point is indeed labeled as an x. So you can imagine that the data that's on the screen right now, this is data that I already know the answer to. I already know that this thing is an x, and I already know that it is at 0.48. Now I'm trying to get my network to learn that fact and be able to tell me that fact in the future. Okay, let's also do our O example here. So now we have our x is 5 and our y is 3. So we have 3 minus 5. I'm so sorry for the people on Zoom because I'm sure you can't see this. What is 3 minus 5, everybody? Minus 2, that's right. Is that above or below 0? That is below 0, right? So we would classify that as O, and that is also a correct classification. So we're doing good so far. Now, what if I have this next x over here? Okay, what is going to happen here? Let's run this through our little equation here. So this time I have my y is 9, and my x is 10. What does this equal? Minus 1. That's right. Is that above or below 0? Below 0. And so what would my network classify this as? It would classify this as an O. Is that the correct answer? No. Oh no! It got the wrong answer. But never fear, because machine learning is here. What we would actually want to do, we're going to want to move our line so that our x is now on the correct side of the line. And what we can do is we can just modify our weights. We had 9 minus 10 equals -1. Now, there are some hidden things that I'm not writing up here right now because they're all equal to 1, and these are our weights. So really what I'm doing here is I'm saying 9 times 1 minus 10 times 1. And what's cool about this is I got this answer -1, and we figured out that this was the wrong answer, right? So we ended up minus of where we should be. We ended up lower down than where we should be. And what we can do is we can figure out which one of our terms caused this problem, right? We know that it was this -10 that gave us the wrong answer, right? It was pointing us in the wrong direction. If we had listened more to this first one, then we would have gotten the right answer. So what we can do is we can reduce how much we listen to that input. Instead, we can say, well, what if we just reduce the weight of that input? We reduce how much we listen to that input quickly. And what that would give us is a line that looks like this, right? Because now, if I run this equation, what is my answer? Made the math really easy for y'all. Yeah, so what is this term? 9, what is this term? 8, yes, and that equals 1, right? And so now, classify this as X, and this is all good. So I understand that this may be a really simple example. And you'll be like, well, how does this relate to machine learning at all, Dave? Like, what's going on here? But this is actually what underlies the heart of all of machine learning. Because what happens here is we have a single perceptron. We have a single layered neural network, and that's going to make us one single line. And it's going to be able to tell us if things are above and below that line. But does somebody want to tell me what happens when I add more neurons, when I add more things to my network? What can I start doing? So if I just ignore everything except for the blue circle, the 2 inputs in the blue circle, what do I know that I get? If I just look at this network and pretend that the red circle and the green circle don't exist, what do I have? Yeah, I have a single line. Okay, let's do that same thing again. What if I ignore the blue circle and the green circle? What do I have? Another line, yeah. So what I've actually ended up with here are 2 lines. Now that's interesting, but that's not incredibly helpful. But since I've thrown this extra neuron on the back, this green one, what do we think that's doing? So what we can do is we can start kind of reducing this down to its parts again, right? If we ignore now the inputs, so if we ignore this input, and we're just left with these 3 things again, what do we have? What does that look like? A line, exactly. We have 2 inputs in a line. Now, before, our inputs were where our thing is on our graph, right? What are our inputs going into that green neuron? What are the outputs of the blue and the red circles? Specifically, yes, above and below. The output is going to be, is it above or is it below my line? So what we actually end up with is basically a second line that is a combination of our first 2 lines. And so we can start basically doing logic with this. We can say, like, if it is, so this green line would basically be asking the combination between everything that is below both of the lines, right? So this is below the blue line and below the red line. And so I've started making this curved line. And what's really neat about this is that I can keep doing this pretty much forever. This is what machine learning does, is it allows us to create more and more and more lines and classify our data in more and more precise ways. It's a little bit like calculus. You can just adding lines until you get to essentially infinity. Now, we can't quite do infinity because we can't make an infinitely large network, but we have proven that a sufficiently large network can approximate any given function. So any mathematical function in existence, we have a math proof that I cannot do it in front of you, but we do have a math proof that says our sufficiently large network could approximate that function. So we can really start to classify any data set that we want. What happens when we start adding more inputs is that we scale the number of dimensions. So with 2 inputs, we have this nice 2-dimensional graph. With 3 inputs, we'd have a 3-dimensional graph. And with 4-dimensional inputs, I can't show you an image of it. And this is where the power of machine learning really starts to come in, is that I might not just have 2 or 3 inputs, I might have a couple of thousand. And I don't know about you, but I would have a really hard time figuring out where the split in a piece of data is when I have a couple of thousand dimensions. And so what machine learning is really doing is it makes something called a hyperplane. In 2 dimensions, that hyperplane is a 2-dimensional line. In 3 dimensions, that is a 3-dimensional plane. And in 4 dimensions, again, we can't really show it to you visually, but it's doing the same thing in 4 dimensions. It's basically taking that data and it's splitting it into pieces. And what's really fun about this is that we can know what direction we need to change our network in. So now I've simplified things a little bit, and we kind of pretend that we only have one dimension of our weights. And we also have this y-axis of how many answers did we get correct. And what we can do is we can follow this slope of our line. So here in this question, I knew what direction I needed to move to improve my score. We can do the same thing across any dimensions. We can figure out which direction do we need to move, which weights do we need to update in which way in order to get us closer to the more correct answer. And this is what's going on here. So you can imagine it like climbing a hill, but you're blindfolded and you don't know where the top of the hill is. You can't see it, but you can take a step and figure out if you've gone up or down. And you basically keep doing that and eventually you'll reach the top of the hill. Now there are exceptions to that, but we're not going to go into that right now. So all of that in summary. Let's take a step out of the math here. Let's go into the big picture. What is a neural network doing? First, we take in some kind of data. We have a set of data that we know what the answers are, usually. It's not all cases of machine learning, we know what the answers are, but in most cases, we have some kind of labeled data set. We have a set of data and we know what we want that answer to be. I know that I had an X at a certain coordinate and I wanted it to be an X. And so I could train my network with that. So we take that data in and we give our network a test. We say, try to answer these questions. Try to give me the right answers on this test. Then we give it a score. And usually that score at the beginning is not very good. But what you do is then you give it the answers and you say, okay, now adjust. You know which directions you need to move in. So take a small step in the right direction and then you test again. And you keep doing this until eventually your network is a star student. Any questions on this? Yeah, definitely. That is a fantastic question that we are going to answer later on tonight after we play with these things a little bit. So as we go into the next section, we're actually playing with these things. I encourage you to ask that question in your head. Say, how would I actually grade this on how well it's doing? And then after that, we'll talk about some of the methods that are used to do that. That was a great one because that is one of the hard problems of machine learning is how do I give it a test? And a lot of the time, this is also where bias in machine learning can start coming in, because a lot of the time it's going to be some kind of human making a value judgment saying this answer is better than that answer. And we might not have like a logical mathematical reason for saying that. It's just a human saying, I like this answer better. So you think of like what that means for things like college applications or loan acceptance. Okay, any other questions on perceptrons and basic neural networks? No, we all want to do something. Okay, let's do something. So we're actually going to go into our activity. So I hope that everybody has a computer or a phone or something with them, an electronic device. If not, I encourage you to find a friend. You can do this in pairs, absolutely. So what we're going to be doing tonight is we're going to be using image generators. So you might have heard of these recently. These are three of the more popular ones lately, and they basically take in a text prompt and output an image for you. And we are going to be doing this. We're going to be making a collaborative choose your own adventure story. So how this is going to work is I have a kind of example here for you. This is going to be the one that we're all working on together. And this is the adventure of Robbie the robot. And I'll be putting up the link for people in a second. So what we can do is you can start by beginning the adventure. And you can see like Robbie is told about a cool event that the CSS is putting on. And Robbie here can either decide to go to the event or decide to stay at home and watch TV and study. Now, right now, I don't have these links going anywhere, but kind of the point of a choose your own adventure story is you're given some kind of text prompt. And then the user is given some kind of decision what they want to happen next. And Google Slides is kind of fun for this because you can link easily to other slides. So I've also created 2 other slides here. And so what I can do is in order to edit this one and link it to a decision, I can either use the shortcut Control K or Command K, or I can say insert link. And you can say it kind of gives some examples here. Now, usually it counts. So if I search in, here we go. So slide 3 is the one that I want to go to here. Usually it also, I think an option here is cut off. Usually there's also one for things in this slide. So I can say, there we go, slide 4. So now if I try this again, we can see, oh, let's go back to the beginning. We begin our adventure. And one option, is that Robbie decides to stay home and watch TV and study. And in this case, kind of the story comes to a bit of an end. Robbie decides to stay home for the night. Instead of going out to the super cool event, they put on Netflix in the background and open up their book to study for an upcoming midterm. But they forgot that you can't multitask like that. And so they ended up being neither productive nor entertained. However, if we go back in time here and we begin our adventure again, what happens if Robbie decides to go to the event? Well, Robbie has to decide how they're getting to the event. And this is where your role in creating this story is going to start. You can see that I have put in 3 options for you here. Robbie either walks there, flies there, or takes a rocket ship there. You decide what happens next. We're going to be creating this story together. So really the only rules are going to be not to delete other people's work, but you're free to just add whatever extra branches you want on top of that. We're going to be doing like a choose your own adventure branching story here. So these are our links that we want to do here. So very quickly, I know I'm going to take you away from it for a second. We also have this link to Stable Diffusion. So Stable Diffusion is one of these image generators. This is a free one online. If you scroll down a little bit, what you can see is that you're going to have this image. So I might be able to enter a prompt like a robot riding a rocket ship to the moon. If we wait a second, this is going to generate a couple of images for us. Let's see how good they are. Hey, look at this. Robot riding a rocket ship to the moon. And what you can do is you can just basically copy this image and then throw it anywhere in the Google Slides. So these are our links. You can either use a QR code or use these bit.ly links and head on into this. There is also this third link. This takes you to another version of Stable Diffusion. This one you have to make an account for, and you get like 100 free generations if you want. It has a couple more options, which is also fun. Any questions on what you're supposed to do? I'm going to take that as a no. All right. Put on some music, and then we're just going to be doing this for about the next 30 minutes or so. We're going to be playing around with this, and I want to see what we get at the end. Yes, thank you so much, Ray, for posting the links in the chat. Really appreciate that. There we go. I'll be walking around and answering any questions people have. I'm very curious to see what we end up coming up with here. So. My friend. I just have another link to show you all here. This is one that has 100 different art styles that you can specify. This is specifically for Stable Diffusion, but you can use it for the other ones too. So if you want to know a bunch of different art styles, you basically just like look through this document here, and it just has a whole whack of them. So you can start having fun with that. And that is at this link here. All right, everybody. So hopefully we all had a lot of fun generating some artwork and having our making our adventure. So what I was going to do up here at the front is kind of do a little bit of a crowdsourced version, a little bit of a show and tell. We're going to do votes on which option we want Robbie to take, and we're going to see where it leads us and see what kind of work we end up with. So I just want to make sure online people can hear us fine, hopefully. Okay, so Robbie is told about a cool event the CSS is putting on. Hands up for Robbie decides to go to the event. 9, okay. Hands up for Robbie decides to stay home and watch TV and study. Not very popular. All right, Robbie decides to go to the event. Robbie has to decide how they're getting to this event. Hands up for walking there. 1, 2, 3. All right. Robbie flies there. 1, 2, 3 as well. And Robbie takes a rocket ship there. Yeah, we got 7 or 8 there. The audio is a bit robotic. Not sure what I can do with that right now. Perhaps I can change my microphone. Is this any better? Hopefully. Okay, so Robbie enters the spaceship and decides whether to travel sublight or use the hyperdrive. Which one do we think he does? Does he use sublight or does he use the hyperdrive? Sublight, hands up. Everybody wants the hyperdrive? Okay. Hyperdrive. That's a very interesting image. Does somebody want to share what prompted they use to do this image?
I use hyperspace.
Use hyperspace. All right, oh, that's an interesting one. So Robbie ascends beyond space and time to become one with the universe, and then still makes it on time to the CSS. I guess if you could travel through time, it's true. You could be anywhere that you want in time. All right, that was an interesting one. I'm going to look through here. What are some of the other potential branches that we could have gone? We could have ended up in sublight travel with laser attacks and being late to the event. Why is the raccoon in a banana car? Robbie stays home for the night. No, I know this isn't the correct order. I kind of just want to like go through it. It's almost more fun out of order. So we have Robbie walks there. Did somebody generate this raccoon? That's pretty good. What else? Robbie goes home. Oh my goodness. Wow, we have a lot on raccoons here. Raccoon sushi. Yeah, these raccoons are very accurate. I am impressed. What else do we have? Raccoon is offended and fights Robbie. Yeah. Oh my goodness. Wow, this is one of a space station. This one is very good. Does somebody want to share what they did with this one?
I don't remember the specific thing, but I think it was like realistic robot takes a spaceship to the International Space Station or something like that.
Okay, realistic robot takes a spaceship to the International Space Station. Wow, that's pretty good. What else do we have here? Sitting on the couch, Netflix in the background, robot. Goes the Wikipedia rabbit hole. Wow, yeah, that truly does look like I feel like that looks more like a Reddit rabbit hole than a Wikipedia one, but favorite human, skincare. Oh my goodness. There's a lot of raccoons here. There's a higher representation of raccoons than I was anticipating. And the raccoon runs away. So that was very interesting looking at that. Does anybody have any questions or comments they'd like to talk about with the art? How do people find it overall? Better, worse than you're expecting? Yeah.
It's definitely like way better.
Yeah. Is that a shared feeling amongst most people? What were some of the things that surprised you about it? What do you think it did well and what do you feel like it struggled with? Okay. In what way do you feel like it? Okay. So you get like at least like the subject of the okay.
I was really surprised that it got my action correct. Like there's a laser attack. So it didn't simply put together a laser and like a space shuttle. It actually animated the like attack effect and the like, reflection of laser. I was surprised.
Oh, interesting. So it didn't just get the subject right, but oftentimes like whatever verb was in there too, like whatever action was also represented fairly accurate. That's interesting.
We got all work.
So it's like it kind of got it, like it was still like transferring a rock to a raccoon, but in the wrong way. Oh, that's interesting. So it kind of got halfway there. Right. Any other observations? Yes, Ray.
I don't know if this is intended to be about both the like Dolly Mini thing or also us as a machine, but like in my pedagogical experience, like it took us a while to sort of figure out, okay, this is what we're supposed to figure out how to do it. You see like different ways of interpreting the same thing. And it was almost like this meta reflection of what the AI was doing, where like some of us were copying just the same title, some of us were interpreting the title in the next slide and creating like different styles of trees. And it was almost like we were trying to be this collective AI from separate agents.
Okay, yeah, so there's like some interesting self-organization and coordination going on amongst the people as well as the AI that we were using. People were like working on the next thing that you would generate, like even before you would get there, maybe. That's kind of fun. Did people like this activity? This is actually my first time. In the past, I've done it with individual people or like small groups. Do people like doing it as just mass chaos? Everybody is involved. Sounds like a lot of fun. Okay. Any other final comments on the activity? All right, let's talk about how this thing actually functions. So let's actually talk about creative AI and how the heck did this thing work? How did it take a text prompt and actually turn that into an image? And how does that relate to what we were talking about earlier, where we kind of have neural networks and we have some kind of input and output and test relationship there? So the first thing that I want to talk about is contrastive language image pre-training. This is a relatively new kid on the block in 2021. Most people just call it CLIP because that name is a mouthful. And basically what it does is it scores image and text pairings. And this is a successor to ImageNet. So ImageNet, if anybody hasn't heard of it, is a giant labeled database of images. Somebody started working on it in, I think, like 2010 or 2012, and it became basically the foundation of all modern computer vision, because it's what finally gave us all of the data that we needed to start training. This is where we started having this fundamental insight of, like, if you've heard the term big data, ImageNet is really what started that trend, where there was a researcher, Fei Li, maybe. She was basically spending her entire PhD and postdoc just working on getting people to label images. And everybody told her that she was totally wasting her time, going to lead nowhere. And then finally, that group was the one that finally broke records on image recognition. This was in 2012. This is a huge paper that came out then. And this is really what started the kind of AI revolution in the 2010s or so, was this realization that if you had a bunch of labeled data, you could train something on that labeled data with these huge networks and then actually create something. CLIP is a bit of a successor to ImageNet, where it doesn't just have image and a labeled data, like a caption of what that image is. It actually also scores how close it is to that image. So you might end up with something like, it's a little bit small there, sorry, but you might have like a picture of a television studio. The correct prompt was chosen and it says a photo of a television studio, but some of the other ones are like a photo of a podium indoor, a photo of a conference room, and those are labeled wrong. So how this works is if we take an image and you take that image and you encode it somehow. So usually that's, you take each individual pixel value and you encode it as inputs to your network. And then you also have some kind of text input with a text encoder, and you also encode that text. So you take both of these things as inputs to your network and you rank your output, your predictions. But instead of just having a 1 and 0, which you can kind of see here, it usually ranks it on a percentage value. It says how close were these two things together. And it does this by drawing off of things like ImageNet, where you have this huge database of a bunch of images and a bunch of captions put together. And it basically ranks these for how similar they are. And then you compare it to what the actual label was. And so with that, you gradually train your AI. And this is really what has, in the last couple of years, given rise to all of the image generators that we see now, is something like this, because this is what's fundamentally used to train an image generator. Is you give it a text prompt, it outputs an image, and you have to say, how close are these two things together? So there are two main ways right now of creating images. The now older kid on the block that's not as popular is something called a generative adversarial network, or a GAN for short. And the way that this one works is you actually have two neural networks together, and they compete with each other and give each other feedback. So the way that you can imagine this is, imagine that you had two networks. One is a generator and one is a classifier. And your goal here is you want to create artificial money. You want to create money that looks like real things. You're trying to counterfeit money. The generator is trying to create images of money that looks like the real thing. It's basically trying to make money that it can pass off as legitimate tender. And the classifier is trying to determine what is images of real money and what is images of fake money. And these two things compete against each other. So the reward functions are opposite to each other, because the classifier is trying to figure out, is this real money or is it fake money? It gets rewarded if it can tell what the real money is and what the fake money is, if it can correctly separate those two. And the generator gets rewarded the closer its money looks like to real money. The classifier will usually like a confidence ratio. It's like, I am 70% sure that this is real money or this is fake money. And you use that to then train the generator, which uses that as feedback for, did I do a good job at making this look like fake money? And so you continue this circle for a while, and they basically reciprocally improve each other. As one gets better, it gives better feedback to the other one and gives better training data to the other one. So as the classifier gets better, it gives better feedback to the generator. And as the generator gets better, it starts giving harder and harder examples to the classifier. So it also gets better at determining the small differences. And at the end, you throw out the classifier, you say, I don't care about that thing, and you're just left with a generator. And the generator can then generate images of things for you. If you combine this with something like Clip, instead of just being able to generate a single thing like money, like a static prompt, you might actually be able to give it multiple images of prompts. The new kid on the block is something called a diffusion network.
My question is, what would some of the flaws of GAN that kind of...
GANs, they look blurry. They're able to get close, but not quite all the way there. I'll show an example of one later, and you can see what it is that we're talking about with that. They were very good, and up until about 2020, they were the best thing that we had, and people were getting really excited about them. But since about 2020, a new thing came out called diffusion networks, and it uses a totally different way of training images, which I think is fascinating. And I would have never come up with this in a million years. You remove noise from an image. So how this works is you start out with a noisy image, something that is just totally random noise. And then you put it through a network and you give some kind of text prompt like Clip, and you say, okay, remove just a little bit of noise from this picture. Show me what this noisy picture with this prompt would look like with just 1% less noise. And then you keep doing this again, where you then give the slightly less noisy picture and you run it through the network again. You say, okay, now take this same prompt, run it again with slightly less noise, with slightly less noise, with slightly less noise. And if you do this again and again and again, what you end up with is something that actually looks like a real image. And how you train this is you start with an image and a prompt, kind of like the ImageNet again, and you add just a little bit of noise. And then you train the network to get back to the original image. And you do this with a whole bunch of different images. And it gradually gets good at figuring out how to get back to the original image with a specific prompt. And what you do then is you keep doing this until eventually you get to the point where you can just give it a noisy image that has no original image at all. You just give it noise and a prompt, and it'll generate an image for you. It's totally fascinating and very unintuitive. You would never think that you'd start with just pure Gaussian noise to get to an image, and yet this is exactly how diffusion networks work. And so these things started appearing in like 2020, and that's why since then we've just seen this huge leap forward in image generation. And that's why you see things like Midjourney, Wombo Dream, like Stable Diffusion, and like Dolly come out in the last year or two. It's because of these diffusion networks. And so I really want to highlight how fast this has really moved. What we have here, this is from 2013. Has anybody seen images like this before? Yeah. Does anybody know what this is?
Like illustrated dogs.
Yes, you're totally right. Yeah, this is Google's Deep Dream, an image recognition software that they trained to recognize dogs, and they couldn't really get it to work. And so one of the engineers was like, you know what, let's try running this backward. Let's see what the network is seeing. And so what you got was this really weird pattern recognition thing where it would actually enhance the dog in a picture. Instead of saying, is this a dog? It would say, this is an image, find the dog. And then they just kind of like turned that up to 11, where they're like, okay, now enhance the dog, make it more dog-like. And you got these really, really weird, psychedelic, almost nightmarish images, which was really, really interesting. Then in 2018, this was generated by a GAN that was trained on 15,000 portrait pieces from 14th to 19th centuries. This was one of the first, basically NFTs before NFTs existed. This is one of the first AI-generated artworks that sold, and it was expected to sell for $7,000 to $10,000, and it ended up selling for $432,500 at auction. And it's just a blurry image. This is what GANs were able to create, is it was trained on a bunch of Renaissance artwork, and then it would recreate this. In 2020, this is the NVIDIA landscape one. So you give it a painting of an image, and then it would fill in what it thinks that would look like. So this is actually one that I like, some mountains and a river and a bridge. And it was pretty fun overall, but you can see it's still kind of blurry, right? You can see this river doesn't quite work. Trees are very low fidelity. The mountains and the mist in the background are like, yeah, but it does sort of look like a blurry landscape image. Maybe if I took it on one of those old dollar store film cameras you get for like $10 on vacation, but generally works. This is an image from Midjourney from 2022. Does anybody recognize this image? This has raised really big controversy in the last couple of months here. It did. Yes, it won the Colorado State Fair for 2022 against human artists. It was made by an AI, and they won this entire state fair. And while you might say like a state fair is not a big deal, it doesn't really matter. People are up in arms about this because they're like, a human didn't make this. You didn't make this. You shouldn't win this. This is a human contest. And they're like, well, nowhere in the rules was there a limitation on what technology I could use. So it sparked this really interesting debate about ownership and authorship, and are artists being replaced by AI generated art? I think that this brings up some really sticky ethical questions that suddenly aren't theoretical anymore. Like, what happens when AI is winning art competitions? But I just kind of wanted to show this progression in that just the last decade, how far we've come, and even in the last 2 years, in the fidelity of these images, just how much of a leap there has been. I personally would not be surprised if we had fairly photorealistic looking videos within the next couple of years. Okay, well, let's talk about careers in AI, because everybody here is in Cogs and we're not afraid of AI. We all want to know how we can make our careers in this thing, because we embrace the future of our machine overlords and we don't shy away from it. What are some of the different careers in AI? I was generally finding that they fall into 3 broad categories. We approach things through a business perspective, through an engineering perspective, or a researching perspective. And underneath here, I have some more specific categories. And while I did put them in columns of relating to a specific thing, the categories truthfully feel a little bit more fluid from that. So in the business category, there's of course entrepreneurs. You're able to find a problem that you think can be solved with machine learning or solved with AI. You create a company, a bunch of people invest money in it. So that is one route. Another route, which is one thing that I found that a lot of Cogs graduates end up in, is project management. What Cogs students tend to be really good at is we're kind of a mix between artists and scientists, and we're not really either one. But this allows us to communicate with a lot of different types of people and people from a lot of different backgrounds, and really act as a translator. In a lot of your Cogs classes, you're really exposed to new ways of thinking a lot and new terms a lot, and you have to translate between disciplines and terminology. And that's something that you're familiar with, bumbling your way through and getting good at. And this is something that project management really relies on as a skill, because project management, you're going to be in charge of a team of some group of people, usually technical people like engineers or researchers, but you're also going to be responsive to business management. And you have to decide, how do I translate between these two worlds? How do I describe what the technical things that my team are doing to the business owners? How do I align the business directives of this place with the actual technical requirements? And I'm almost surprised with how many Cogs students end up in some form of project management or another. And AI especially if you have an understanding of how it works and what its limitations are, enough that you can discuss with an engineer. You don't need to understand the specifics, but if you can discuss and follow a conversation with an engineer, but still understand the business implications of this, the ethical implications of this, that's a really interesting one. Another one is business intelligence. And this is exactly what it sounds like. It's just using AI specifically to make business decisions. It's a big problem. How many orange juice do I need to order and stock inside of my grocery store today? That is a legitimate problem. And things like logistics can fall into this as well. AI is really good at predicting patterns in data. If you have a lot of data, if you can find a way to make that even a little bit more efficient, there's a lot of people that are interested in it. In the engineering side, there is physical robotic side of it, trying to physically instantiate things. Cogs students, I find, don't tend to go this route as much. You'll see more engineering students do that, but I have seen some Cogs grads go in more of the robotics way. And there's also the more technical engineer side of things as well. So that diving really deep into the algorithm, into the data, how do you actually make this thing work? And then there's also a developer. And this is one that, again, I feel like Cogs students could fall into, because even though the distinction between developer and engineer is a little bit different, at least the way that I see it is an engineer is really getting into the nitty-gritties of the algorithm and is like, how do I make this thing work? Whereas a developer might be more using an API, using the final algorithm to accomplish something. So if you've taken Cogs 300, you will have used the Unity machine learning agents API. Well, you weren't the one actually going and making this reinforcement learning algorithm. You weren't going into the nitty-gritties of the network and the weight, but you were using this network to then train something and make it do a specific task. And that's something that, again, Cogs students can be good at, is maybe not necessarily going into building the algorithm itself, but using the algorithm for some real world application or theoretical application. Finally, on the research side of things, there's, of course, a data analyst. This one is really big. How do you actually get good data? There's a famous saying in computer science, garbage in, garbage out. It doesn't matter how good your algorithm is. If your inputs are crap, your outputs are also going to be crap. And so there's a big emphasis on how do we get good data? How do we actually structure that data? What things do we need to look at? How can we be planning ahead so that 4 or 5 years from now, we might be able to solve this problem? Because sometimes a big thing in machine learning is, well, we don't have the data right now to be able to solve this problem. So what data would we need? Okay, let's start collecting that. And you might have to actually plan a couple of years in the future to get that data. And that is, of course, a bit of an art and a science, but it can get quite interesting. So if you like math and you like statistics, that could be one for you. After that, we have the user experience researcher. Again, this is one that is huge in Cogs. I would say that UX is probably, along with project manager, the one that I see the most Cogs grads going into, because it's kind of a mix between the technical and the psychological. This is one thing that I think is going to grow in the future, especially if you're more on like developer side of Cogs, where you can still understand the algorithm of what's going on. Maybe you don't know how to code it yourself, but you have a bit of an intuition of how do these systems work. The user experience researcher or designer is going to be the person that's being that design interface between the public, people who have no idea what this thing is at all, and then the technical code engineering side. You're like, okay, how do I actually communicate this information in a way that somebody who is not technical can navigate it, can understand it? And so it's really about translating and simplifying again. And then finally, we have an ethicist. And this is one that is also really big right now. How do you make sure that these things are behaving ethically? Especially there's a really big problem with bias in machine learning right now, as we've realized that a lot of data that we have has exposed a lot of our unconscious biases. This is one thing that I think is fascinating about AI, is that it holds up a mirror to humanity, because we might not think that we're doing something, but then an AI comes along and it starts doing things that maybe we didn't anticipate. Well, why is it doing that? It shouldn't be doing that. We don't want it. It's basically learning from human behavior. So one aspect of this, which I think is directly relevant to the AI image generation, is gender ratios in different types of images. I know the DALL-E, OpenAI, has talked about it, is they try to screen their images for not safe for work. They try not to have things like nudity or violence. What they also found is that by doing this, by filtering out any not safe for work images, they were getting underrepresentation of women in their pictures, because a lot of pictures of women on the internet involve nudity. And they didn't want their network to do that. And so they were having trouble still getting equal representation across their images. They've improved on it now, but especially if you did this 6 months or a year ago, if you typed in things like computer scientist, like doctor, you'd almost universally have a man in that picture. And so this has been really interesting, I think, and really holds up this mirror to humanity because it shows us through our actions how we are behaving. There's really no way around that. This is the data. This is what happens when you look at human behavior. And so there's a lot of really sticky ethical questions in there that I think are really interesting to explore going into the future. Then I think that this is a good point to translate into the ethics of some of these. I have some question prompts for us here. We're really trying to ask what types of impacts are these going to have on the world? Again, I think we've really moved from the theoretical future impacts here to impacts that are happening in the world today. Sometimes we get so caught up in thinking whether or not we can make something that we forget to ask, should we make this? For discussion number one, I wanted to talk about copyright law, intellectual property ownership, and how this affects things like artist job security and compensation, as well about artists whose artwork may have been used to train the model and they're not compensated for that. Even if you can explicitly go in and say, I want artwork in the style of this artist. If we get in groups of 2 or 3, I was gonna do 5 minutes in discussions of groups 2 or 3, and then we'll slowly get larger and larger groups and then finally come together. Chat about this question. How does AI art specifically affect copyright law? And then you might want to take the discussion even beyond AI art. We are going to do this as our next discussion, which is moving back to the original question of this workshop. Do you think that this AI is creative? And what does this mean for other domains of human creativity? All right, everybody. I'm just going to get your attention up at the front quickly. I know that we all still have wonderful, interesting ideas, but it is past 8 o'clock, and I want to make sure that I give people the opportunity to leave. Although I doubt anybody else is coming into this room in the near future. So if you made a new friend and you want to debate with them longer, then you are welcome to stay here and do so. But hopefully we all had fun at this workshop. Hopefully we all learned something a little bit new about AI, about how it is used in potentially or potentially not creative ways and what impacts that has on the world. So thanks for having me here tonight. You're welcome to come up here and chat with me if you have any questions. You can also find me on the Cogs Discord, which I actually don't have listed up there. Or you can look at my website or find me on LinkedIn. Those are the places that I exist online if you do want to see more of what I do. Other than that, that's it from me. So thanks everybody for coming tonight. I do have one final thing to share. If people do want to stay longer, there's by no means a requirement. I had an extra discussion here, which was about synthetic media's effect on the information ecosystem. So as I'm cleaning up, I do want to give people a chance to go. This is just extra bonus if you want it at all. Thank you very much.